Earth to the edge. What if I told you that right now, at this very moment, you are hurtling through the cosmos at a speed so absurd, so incomprehensibly fast, that if you could actually feel it, you would be screaming in terror? You are sitting there, maybe on your couch, maybe in your bed, maybe at a desk, feeling perfectly still, perfectly safe, perfectly stationary, but you are not stationary. You are not even close to stationary. The Earth beneath you is spinning on its axis at roughly 1,670 kilometers per hour. That is faster than the speed of sound. You are on a supersonic merry-go-round, and you cannot even feel it. But that is just the beginning. That spinning Earth is also orbiting the Sun at approximately 107,000 kilometers per hour. So, you are spinning and orbiting simultaneously. But wait, there is more. The Sun itself, our star, is orbiting the center of the Milky Way galaxy at around 828,000 kilometers per hour. And the Milky Way? It is moving through the universe at roughly 2.1 million kilometers per hour, pulled by the gravitational influence of structures so massive that we have only recently begun to understand them. So, let me paint this picture for you. You are sitting still, feeling nothing, while simultaneously spinning at supersonic speed, orbiting a nuclear fireball at 100,000 kilometers per hour, spiraling around a supermassive black hole at nearly 1 million kilometers per hour, and surfing the cosmic web at 2 million kilometers per hour. And you feel absolutely nothing. Not a breeze, not a wobble. Nothing. If that does not make you question everything you think you know about reality, I do not know what will. But here is what really gets me. Here is what keeps me up at night. All of that motion, all of that speed, all of that cosmic ballet we are performing every single second of every single day. It is happening inside a universe so vast, so incomprehensibly enormous, that all of our motion is essentially meaningless on the cosmic scale. We are moving at millions of kilometers per hour, and we are going nowhere. We are a speck on a speck on a speck, racing through a void so large that the word large is an insult to its scale. The observable universe, just the part we can see, is 93 billion light-years across. And a single light-year is 9.46 trillion kilometers. I want you to try to multiply those numbers in your head. I want you to try to picture that distance. You cannot. Your brain literally cannot do it. The human brain evolved to understand distances like the river is a 2-day walk from here, or the next village is over that hill. We did not evolve to comprehend trillions upon trillions of kilometers. And yet, here we are, trying. And that is what makes us remarkable. So today, we are going on a journey, not a short journey, not a surface-level, 5-minute summary that leaves you with a vague sense that space is pretty big. No, today we are going deep. We are starting right here, right where you are sitting, on the surface of this tiny blue marble we call Earth. And we are going to travel outward, step by step, layer by layer. We are going to visit the moon, our loyal companion. We are going to plunge into the sun, our personal nuclear reactor. We are going to tour every planet in our solar system, from the scorched plains of Mercury to the diamond rains of Neptune. We are going to drift through the asteroid belt, sail past the Kuiper belt, and venture into the Oort cloud, that ghostly sphere of ice that marks the true edge of our sun's domain. And then, when most videos would stop, we are going to keep going. We are going to cross the interstellar void and visit the nearest stars. We are going to zoom out and see the full majesty of our Milky Way galaxy, a spinning disk of 200 to 400 billion stars. We are going to witness galaxy clusters, superclusters, the cosmic web, and finally, the edge of the observable universe itself. And then, because I know you are curious, because I know the question is already forming in your mind, We are going to ask what lies beyond, what is out there, past the edge of everything we can see. Is the universe infinite? Did it have a beginning? Will it have an end? And what does any of this mean for us, for tiny little us, sitting on our tiny little rock, in our tiny little corner of an incomprehensibly enormous cosmos? This is going to be a long journey. This is going to be an intense journey, and I promise you, by the end of it, you will never look at the night sky the same way again. You will never look at yourself the same way again. Because the story of the universe is not a story about distant things that have nothing to do with you. The story of the universe is your story. The atoms in your body were forged in the hearts of dying stars. The calcium in your teeth, the iron in your blood, the oxygen you are breathing right now, all of it was cooked up in nuclear furnaces that exploded billions of years before you were born. You are not just in the universe. You are the universe. You are a collection of atoms that somehow, against all odds, arrange themselves into a pattern that can think, that can wonder, that can look up at the stars and ask, "What are you?" And that, my friends, is the most mind-blowing fact of all. But we are getting ahead of ourselves. We have a journey to take. So, if you love space, if you love having your mind blown, if you are the kind of person who gets chills when you think about the cosmos, do me a favor right now. Hit that like button. I know it sounds simple, but it genuinely helps more than you can imagine. It tells the algorithm that this kind of deep, thoughtful content matters, that people want more than just short clips and surface-level summaries. Subscribe if you have not already, because we go deep on topics like this all the time, and I do not want you to miss what is coming next. And here is what I really want you to do. Drop a comment right now. Tell me, what do you think is at the edge of the universe? What do you think is out there, past the boundary of everything we can observe? I am genuinely curious. I read the comments. I want to know what you think, because this is not a one-way conversation. We are exploring this together. Now, let us begin. Let us start with the ground beneath your feet. Before we leave Earth, before we take a single step into the cosmos, I want you to truly appreciate where you are. I want you to understand what you are standing on, because most people take Earth for granted. It is just the ground. It is just the place where we live. It is just here. But Earth is not just anything. Earth is a miracle, and I do not use that word lightly. Earth is a 4.54 billion-year-old rock with a molten iron core, generating a magnetic field that shields us from the lethal radiation of our own star. Think about that for a second. Without that magnetic field, the solar wind, a stream of charged particles constantly blasting out of the sun, would strip away our atmosphere. Without our atmosphere, there would be no air to breathe, no pressure to keep water liquid, no ozone layer to block ultraviolet radiation. Life as we know it would be impossible. We exist because a ball of molten iron deep beneath our feet is spinning in just the right way to create an invisible magnetic shield that wraps around our planet like a protective cocoon. You cannot see it, you cannot feel it, but without it, you would not exist. Let me give you some numbers because the numbers tell a story. Earth has a diameter of about 12,742 kilometers. That sounds big, right? It is by human standards. It would take you months to walk across it. But in cosmic terms, Earth is tiny. It is almost comically tiny. If you placed Earth next to Jupiter, it would look like a marble next to a basketball. If you placed it next to the sun, it would look like a peppercorn next to a beach ball. And if you placed it in the context of the Milky Way galaxy, you could not even see it. It would be invisible, less than a speck of dust, less than an atom. It would simply not register. And yet, On this tiny, invisible speck, something extraordinary has happened. Life, consciousness, you. The universe created a machine, a biological machine that can contemplate its own existence, that can ask questions about the universe that created it. Earth is the only place we know of where this has happened. In all our searches, in all our observations, in all the trillions of stars and planets we have catalogued, Earth is the only confirmed home of life. Maybe that will change someday. Maybe we will discover bacteria on Mars or microbes in the oceans of Europa. Maybe we will detect a signal from a distant civilization. But for now, as far as we know, Earth is it. And that makes it precious beyond measure. Here is something I want you to try. I want you to imagine yourself floating in space, looking back at Earth. This is not a hypothetical exercise for astronauts alone. This is a mental exercise for all of us. Picture the Earth from space. You have seen the photos. That brilliant blue sphere swirled with white clouds, glowing against the black void. It looks peaceful, it looks fragile, it looks alive. Every astronaut who has seen Earth from space reports something called the overview effect, a cognitive shift, a sudden and profound understanding that all of humanity, all of our conflicts, all of our borders, all of our politics, all of our history, everything we have ever known is contained on that single, delicate sphere. There is no line between countries visible from space. There is no border between rich and poor. There is just Earth, just life, just us. Carl Sagan understood this better than anyone. In 1990, as the Voyager 1 spacecraft was leaving the solar system, Sagan convinced NASA to turn the camera around and take one last photo of Earth. The result was a picture in which Earth appeared as a tiny, pale blue dot, a fraction of a pixel, suspended in a beam of sunlight. And Sagan wrote words that I believe every human being should read at least once in their life. He wrote, "Look again at that dot. That is here, that is home, that is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." Those words hit different when you understand the scale of the universe, and by the end of this video, you will understand it. Now, let me give you one more fact about Earth before we leave. A fact that illustrates just how thin the boundary is between our safe little world and the deadly void of space. If you could get in your car and drive straight up, at highway speed, you would reach space in about 1 hour. 1 hour. The Kármán line, the internationally recognized boundary of space, is 100 kilometers above sea level. That is it. 100 kilometers. The distance many people drive to work and back every day. Our atmosphere, the thin shell of gas that keeps us alive, that gives us air to breathe and blue skies to admire, is thinner relative to Earth than the skin of an apple is to the apple. You are living inside a paper-thin bubble of air clinging to a rock hurtling through the void. And outside that bubble is a vacuum so cold and so lethal that you would lose consciousness in about 15 seconds and be dead in about 2 minutes. Welcome to the universe. It is beautiful, but it is not friendly. Now, let us take our first step outward. Let us visit our closest companion in the cosmic neighborhood. Let us go to the moon. The moon, our moon. That glowing silver disk that has captivated humanity since the very first pair of eyes looked upward and wondered what it was. Every culture in human history has told stories about the moon. It has been a god, a goddess, a calendar, a compass, a romantic symbol, a source of madness, a destination for dreamers. And now, in our age of science, we know what it truly is, a 2,159-kilometer-wide ball of rock and dust orbiting our planet at an average distance of 384,400 kilometers. But those bare facts do not begin to capture how strange, how important, and how beautiful the moon really is. Let me hit you with something that most people do not realize. The distance between Earth and the moon is so large that you could fit every single planet in our solar system in that gap. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, all of them, lined up in a row, would fit between Earth and the moon with room to spare. Let that sink in. Every planet, every gas giant, every rocky world. They all fit in what looks to the naked eye like a trivially short distance. The moon looks close. It looks like you could almost reach out and touch it on a clear night. But it is far. It is very, very far. And yet, remarkably, the moon is the closest celestial body to Earth. It is the only other world that human beings have physically walked on. It is our nearest neighbor, and by cosmic standards it is practically sitting in our lap. This tells you something important about the scale of the universe. Even the close things are staggeringly far away. So, how did the moon get there? This is one of the great stories in planetary science. The leading theory, and it is beautifully violent, is called the giant impact hypothesis. About 4.5 billion years ago, when Earth was still young and molten and angry, a Mars-sized body called Theia came screaming through the inner solar system and slammed into our planet. The collision was apocalyptic on a scale that makes every disaster movie ever made look like a gentle breeze. The impact liquefied both bodies, blasting an enormous amount of debris into orbit around Earth. Over time, this debris coalesced, clumped together, and formed the moon. So the moon is not just our companion. It is a piece of us. It is made from the same stuff as Earth, forged in the most violent event our planet has ever experienced. And here's what makes it even more incredible. Without the moon, you probably would not exist. The moon stabilizes Earth's axial tilt. Right now, Earth is tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us seasons. Without the moon's gravitational influence, Earth's tilt would wobble chaotically over millions of years, swinging from nearly 0 degrees to as much as 85 degrees. This would cause catastrophic climate shifts that would make the development of complex life extremely difficult, perhaps impossible. The moon also drives our tides, and there is a compelling argument that tidal pools, those shallow zones where ocean meets land, were crucial nurseries for the evolution of life on Earth. So, in a very real sense, we owe our existence to a cosmic collision that happened 4.5 billion years ago. The moon is also tidally locked to Earth, which means it rotates on its axis at exactly the same rate it orbits us. The result is that we always see the same face of the moon. The far side, often incorrectly called the dark side, is never visible from Earth. It was not seen by human eyes until 1959, when the Soviet Luna 3 spacecraft flew around and photographed it. And it looks remarkably different from the near side, far more heavily cratered, with very few of the dark basaltic plains called Maria that dominate the face we see. Nobody knows for sure why the two sides are so different, but it probably has to do with the moon's asymmetric interior. One side has a thicker crust than the other, possibly a remnant of how it formed in that ancient collision. And then there is the human story of the moon. On July 20th, 1969, 2 human beings stepped onto the lunar surface for the first time. Neil Armstrong and Buzz Aldrin, part of the Apollo 11 mission, walked on another world. Think about what that means. For the entirety of human history, the moon was unreachable. It was a light in the sky, a symbol, a dream. And then, In the span of a single decade, we went from barely getting into orbit to standing on its surface. The Apollo program remains, in my opinion, the single greatest achievement of our species. Not because of the technology, though the technology was remarkable. Not because of the science, though the science was groundbreaking, but because of what it represented. The idea that human beings can look at something impossibly far away and say, "We are going there," and then do it. When the astronauts looked back at Earth from the moon, they saw their entire world, everyone they had ever known, everything humanity had ever built, hanging in the blackness of space. It was small, it was fragile, and it was home. That is the overview effect I mentioned earlier. It changes people. It changed the astronauts. And I believe that if every person on Earth could experience it, even for a moment, it would change us too. One more thing about the moon before we move on. Light takes 1.3 seconds to travel from the moon to Earth. That is practically instantaneous. When Neil Armstrong spoke from the lunar surface, his words took just over a second to reach Mission Control in Houston. But as we move outward, these light travel times are going to get longer. Much longer. Incomprehensibly longer. That 1.3 seconds is going to become 8 minutes, then hours, then years, then thousands of years, then millions, then billions. The distances are about to become absurd. And the moon is just our first stop. Now, let us turn our gaze toward the blazing heart of our solar system. Let us visit the sun. Every morning, you wake up, and if it is a clear day, you see a bright yellow-white disk in the sky. You take it for granted. It is just the sun. It rises, it sets, it provides light and warmth. But here is what the sun actually is. A sphere of hydrogen and helium 1.4 million kilometers in diameter, so massive that it contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust, it all makes up the remaining 0.14%. The sun is the solar system. Everything else is just debris caught in its gravitational pull. Every single second, the sun converts approximately 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, that mass is converted directly into energy, according to Einstein's famous equation, E equals mc squared. 4 million tons of matter annihilated every second and converted into light, heat, and radiation. And the sun has been doing this for 4.6 billion years. It will continue doing it for about another 5 billion years before its fuel runs out. It is the most sustained, most powerful, most reliable energy source in our cosmic neighborhood, and it operates on a principle that we are still struggling to replicate here on Earth. Nuclear fusion. Let me take you inside the sun for a moment, because what happens in there is truly one of the great wonders of physics. At the sun's core, the temperature is approximately 15 million degrees Celsius, and the pressure is so intense that hydrogen atoms are squeezed together until their nuclei fuse. This is the proton-proton chain reaction, and it is the engine that powers our star. 4 hydrogen nuclei, which are just protons, are crushed together to form one helium nucleus, releasing an enormous amount of energy in the form of gamma-ray photons and neutrinos. Now, here is where it gets really interesting. Those photons, those packets of light energy born in the sun's core, do not simply shoot straight out to the surface. The sun's interior is so dense that each photon is absorbed and re-emitted trillions upon trillions of times, bouncing around in what physicists call a random walk. The result is that a photon born in the sun's core takes approximately 100,000 to 200,000 years to reach the sun's surface. Let me say that again. A single photon, traveling at the speed of light, takes 100,000 years to fight its way through the sun's interior and reach the surface. But once it breaks free, once it erupts from the photosphere and enters open space, it takes only 8 minutes and 20 seconds to cross the 150 million kilometers between the sun and Earth and hit your face. So the sunlight warming your skin right now was born in a nuclear fusion reaction 100,000 years ago, trapped inside the sun for longer than modern humans have existed, and then made the final sprint to Earth in about the time it takes to boil an egg. You are being warmed by ancient light. The sun's surface temperature is about 5,500 degrees Celsius, which sounds hot, and it is, but it is almost cold compared to the corona, the sun's outer atmosphere. The corona reaches temperatures of 1 to 3 million degrees Celsius, and nobody fully understands why. This is one of the great unsolved mysteries in solar physics, the coronal heating problem. How can the outer atmosphere of the sun be hundreds of times hotter than the surface? It is like walking away from a campfire and finding that the air gets hotter the further you go. Various theories exist involving magnetic reconnection, wave heating, and nanoflares, but the complete answer remains elusive. The sun is right there. We can see it every day, and we still do not fully understand it. Now, let us talk about size, because the sun's size is genuinely difficult to comprehend. 1.3 million Earths could fit inside the sun. Let me give you a better comparison. If the sun were a standard front door, Earth would be the size of a nickel. If you could drive a car at highway speed around the equator of the sun, it would take about 6 months. Around Earth? About 17 hours. The sun is enormous. But, and here's the twist that starts to change your perspective, the sun is actually a pretty average star. It is a G-type main sequence star, which means it is medium-sized, medium temperature, and medium brightness compared to the full range of stars in the universe. There are stars out there that make our sun look like a grain of sand next to a skyscraper. We will meet some of them later, but for now, understand this. The thing in our sky that is so bright you cannot even look at it directly. The thing that powers all life on Earth. The thing that contains 99.86% of our solar system's mass is a perfectly average, unremarkable star, and there are at least 200 billion more of them in our galaxy alone. The sun also has a lifespan, and knowing that lifespan tells us something about the future that is both scientifically fascinating and existentially unsettling. Right now, the sun is about halfway through its main sequence life. It has been burning hydrogen in its core for 4.6 billion years, and has enough fuel for roughly another 5 billion. But as it ages, it will slowly get brighter and hotter. In about 1 billion years, the sun's increased luminosity will cause Earth's oceans to evaporate, ending life on our planet long before the sun itself dies. In about 5 billion years, the sun will exhaust the hydrogen in its core, and what happens next is dramatic. The core will contract and heat up while the outer layers expand enormously. The sun will swell into a red giant, engulfing the orbits of Mercury and Venus, and possibly Earth. Our home, everything we have ever built, every trace of human civilization, could be consumed by the dying star that once gave us life. After the red giant phase, the sun will shed its outer layers into a beautiful planetary nebula and collapse into a white dwarf, a dense, Earth-sized remnant that slowly cools over trillions of years. Eventually, in the impossibly distant future, it will become a black dwarf, a cold, dark, dead star. But the universe is not old enough for any black dwarfs to exist yet. The first stars that will become black dwarfs are still slowly cooling. The universe is young, and even death takes an unimaginably long time out here. The sun has a story, and we are living in its middle chapters. Now, let us visit the worlds that dance around it. We begin with Mercury, the closest planet to the Sun, and immediately Mercury hits us with a surprise. You would think, logically, that the planet closest to the Sun would be the hottest planet. It is not. Mercury is not even close to being the hottest planet. That title belongs to Venus, which we will get to in a moment. Mercury lacks a significant atmosphere, and without an atmosphere to trap and distribute heat, temperatures on Mercury swing wildly. On the side facing the Sun, temperatures soar to around 430 degrees Celsius. On the night side, they plummet to negative 180 degrees Celsius. That is a temperature swing of over 600 degrees, the most extreme of any planet in our solar system. Mercury is a world of extremes, baked and frozen in equal measure, with nothing in between. Mercury is also tiny. It is the smallest planet in the solar system, only slightly larger than our moon. It has virtually no atmosphere, just a thin exosphere of atoms blasted off its surface by the solar wind and micrometeorites. It has no moons. It has no rings. In many ways, Mercury seems like the most boring planet, but it holds secrets that have puzzled scientists for decades. For one thing, Mercury has ice. Yes, ice, on the planet closest to the Sun. Deep inside permanently shadowed craters near Mercury's poles, where sunlight has not reached for billions of years, there are deposits of water ice. These craters are so deep and Mercury's axial tilt is so small, just 2 degrees, that their floors exist in permanent shadow, maintaining temperatures low enough for ice to survive. It is one of the most counterintuitive facts in planetary science. There is ice on the closest planet to the Sun. Mercury is also shrinking. Over its 4.5 billion year history, Mercury has lost approximately 7 kilometers of its radius. As its iron core slowly cools and contracts, the planet's surface wrinkles like the skin of a drying apple, creating vast cliffs called lobate scarps that can be hundreds of kilometers long and over a kilometer high. Mercury is a dying world, slowly contracting in the relentless heat of the Sun. And then there is Mercury's relationship with time, which is genuinely strange. Mercury's orbital period, the time it takes to go around the Sun, is about 88 Earth days. But its rotation period, the time it takes to spin once on its axis, is about 59 Earth days. Because of a phenomenon called spin-orbit resonance, Mercury rotates exactly 3 times for every 2 orbits around the Sun. The result is that a single solar day on Mercury, from one sunrise to the next, takes 176 Earth days. So a single day on Mercury is longer than 2 of its years. Time works differently on Mercury. Now let us move to the planet that should terrify you, Venus. If Earth is the Goldilocks planet, the one that is just right, then Venus is the cautionary tale. Venus is what happens when things go wrong. It is Earth's evil twin, and I mean that literally. Venus is almost exactly the same size as Earth, about 95% of Earth's diameter and 80% of Earth's mass. Billions of years ago, Venus may have had oceans, a moderate temperature, and conditions potentially suitable for life. But something went catastrophically wrong. A runaway greenhouse effect took hold. Carbon dioxide accumulated in the atmosphere, trapping more and more heat, which released more carbon dioxide from the rocks, which trapped more heat, in a vicious feedback loop that spiraled completely out of control. Today, Venus has a surface temperature of approximately 465 degrees Celsius. That is hot enough to melt lead, tin, and zinc. It is hotter than Mercury, despite being nearly twice as far from the Sun. And the reason is that atmosphere. Venus's atmosphere is 96.5% carbon dioxide, creating the most extreme greenhouse effect in the solar system. The atmospheric pressure on the surface of Venus is about 90 times that of Earth. Standing on the surface of Venus would be like being 900 meters underwater on Earth. You would be simultaneously crushed by pressure, dissolved by sulfuric acid, which rains from the clouds, and incinerated by temperatures that would melt metal. Venus is hell, literal hell. And Venus rotates backward. Every planet in the solar system rotates in the same direction, counterclockwise when viewed from above the North Pole, except Venus and Uranus. Venus rotates clockwise, a phenomenon called retrograde rotation. Nobody knows for sure why. It may have been knocked upside down by a massive impact early in its history, or tidal interactions with its thick atmosphere may have gradually reversed its spin. And because Venus rotates so slowly, a single Venusian day, from one sunrise to the next, takes 243 Earth days, which is actually longer than a Venusian year of 225 Earth days. So, on Venus, a day is longer than a year. Venus is a world that seems designed to be as hostile and as counterintuitive as physically possible. The Soviet Union was the only nation to successfully land spacecraft on the surface of Venus. The Venera program, spanning from the 1960s to the 1980s, sent a series of landers to Venus's surface. They survived only minutes before being destroyed by the heat and pressure. But in those precious minutes, they sent back photographs of a rocky, orange-tinted landscape under a thick, oppressive sky. Those images remain the only photographs ever taken from the surface of another planet in the inner solar system, other than Mars. They are haunting and beautiful. In 2020, a team of scientists made a stunning announcement. They had detected the phosphine gas in the atmosphere of Venus. On Earth, phosphine is produced by anaerobic bacteria. The implication was extraordinary. Could there be life, microbial life, floating in the clouds of Venus at altitudes where the temperature and pressure are actually quite Earth-like? The detection has been hotly debated, with some scientists confirming it and others unable to replicate the results, but the possibility remains tantalizing. Venus, the most hellish planet in the solar system, might harbor life in its clouds. The universe has a sense of irony. Now, let us move to the planet that has captured humanity's imagination more than any other. Mars, the Red Planet. Named after the Roman god of war because of its blood-red appearance in the night sky, caused by iron oxide, essentially rust, covering its surface. Mars has been the subject of more science fiction, more speculation, more conspiracy theories, and more space missions than any other planet. And for good reason. Mars is the planet most like Earth. It is cold, it is dry, it is bathed in radiation, and its atmosphere is only about 1% as thick as ours. But it has seasons, it has polar ice caps, it has a roughly 24-hour day, and most importantly, it shows overwhelming evidence that it once had liquid water on its surface. Rivers, lakes, possibly even a vast ocean covering its northern hemisphere. Mars was once a wetter, warmer, more hospitable world, and that raises the single most exciting question in all of planetary science. Was there ever life on Mars? Mars is a world of extremes and superlatives. It has the tallest volcano in the solar system, Olympus Mons, which stands approximately 22 kilometers high, nearly 3 times the height of Mount Everest. Olympus Mons is so large that if you stood on its summit, you would not be able to see the edges, they would be beyond the horizon. The volcano's base is roughly the size of France. Mars also has the largest canyon system, Valles Marineris, which stretches over 4,000 kilometers long, up to 700 kilometers wide, and as deep as 7 kilometers. If placed on Earth, it would stretch from New York to Los Angeles. Mars may be a small planet, about half Earth's diameter, but it has the most dramatic geography in the solar system. The search for life on Mars is arguably the most important scientific quest of our generation. NASA's Curiosity rover, which landed in 2012, has found organic molecules, seasonal methane fluctuations, and evidence of ancient habitable environments. The Perseverance rover, which landed in 2021, is specifically designed to search for signs of ancient microbial life and is collecting samples that will eventually be returned to Earth for analysis. Perseverance also carried the Ingenuity helicopter, which achieved the first powered flight on another planet, a Wright brothers moment on Mars. The evidence for ancient water on Mars is now considered overwhelming. Dried riverbeds, mineral deposits that only form in liquid water, rounded pebbles shaped by flowing rivers, clay minerals in ancient lake beds, it is all there. Mars was once a place where life could have thrived. Whether it actually did remains one of the great unanswered questions. And then there is the future. Mars is the most likely candidate for human colonization. Elon Musk and SpaceX have made Mars colonization a central goal, envisioning a self-sustaining city on Mars within our lifetimes. The challenges are immense. The 6 to 9 month journey, the lethal radiation during transit and on the surface, the thin atmosphere that provides almost no protection, the cold temperatures averaging around -60 degrees Celsius, the toxic, perchlorate-rich soil, and the psychological toll of living millions of kilometers from Earth with no possibility of quick return. But the dream persists, and maybe, just maybe, within the lifetime of someone watching this video, a human being will walk on Mars. When that happens, it will be the Apollo moment of our generation. It will change everything. Between Mars and Jupiter lies a region that the movies have gotten completely wrong: the asteroid belt. In every science fiction film, the asteroid belt is depicted as a dense field of rocks that spacecraft have to dodge and weave through at high speed. In reality, the asteroid belt is almost entirely empty space. The total mass of the entire asteroid belt is less than 4% of the Moon's mass, and the average distance between asteroids is about 1 million kilometers. If you were standing on an asteroid in the belt and looked around, you would be hard-pressed to see another asteroid with the naked eye. The belt is vast, and the rocks are small and scattered. Spacecraft pass through it without any difficulty whatsoever. The largest object in the asteroid belt is Ceres, a dwarf planet about 940 kilometers in diameter. Ceres was visited by NASA's Dawn spacecraft, which revealed bright spots of sodium carbonate in the Acator crater, suggesting recent geological activity involving briny water pushing up from below the surface. Even Ceres, a tiny world in the vast emptiness of the asteroid belt, has surprises for us. The asteroid belt exists because Jupiter's enormous gravity prevented the material in this region from ever coalescing into a planet. Jupiter stirred things up so much that instead of a planet forming, we got a collection of rocky and metallic debris, leftovers from the birth of the solar system, a construction site that was never completed. Now, we cross the asteroid belt and enter a different realm entirely. We leave behind the small, rocky, sun-warmed inner solar system and enter the domain of the giants. And the king of the giants is waiting for us: Jupiter. If the solar system were a royal court, Jupiter would be the sovereign. It is the largest planet, the most massive planet, and arguably the most important planet in our solar system. Jupiter has a diameter of approximately 139,820 kilometers. That is 11 times the diameter of Earth. More than 1,300 Earths could fit inside Jupiter. Its mass is 2.5 times that of all the other planets combined. Jupiter is so massive that it does not really orbit the Sun. Instead, Jupiter and the Sun orbit a common center of mass, called the barycenter, which lies just outside the Sun's surface. Jupiter is the only planet massive enough to make the Sun wobble. Jupiter's Great Red Spot is perhaps the most famous storm in the solar system. It is a massive anticyclonic storm that has been raging for at least 350 years, since astronomers first observed it in the 17th century. At its peak, the Great Red Spot was large enough to contain 2 or 3 Earths. It has been shrinking in recent decades but remains an enormous and awe-inspiring feature. Winds at its edges reach speeds of over 430 kilometers per hour. We have nothing on Earth that compares. Jupiter is also a giant ball of gas, primarily hydrogen and helium, with no solid surface. If you tried to land on Jupiter, you would simply sink deeper and deeper into increasingly dense gas, which would gradually transition into a liquid and then into a bizarre state called metallic hydrogen, where hydrogen is compressed so tightly that it behaves like a metal, conducting electricity and generating Jupiter's insanely powerful magnetic field. Jupiter's magnetic field is the strongest of any planet, roughly 20,000 times more powerful than Earth's. This field creates intense radiation belts around Jupiter that would be lethal to any unshielded human. But perhaps the most exciting thing about Jupiter is not Jupiter itself, but its moons. Jupiter has at least 95 known moons, a miniature solar system in its own right. And among those moons are some of the most intriguing worlds in the cosmos. Europa, slightly smaller than our moon, is covered in a shell of water ice. Beneath that ice, scientists believe, lies a global ocean of liquid water, kept warm by tidal heating from Jupiter's enormous gravitational pull. This subsurface ocean may contain more water than all the oceans on Earth combined. And where there is liquid water, there is the potential for life. Europa is considered one of the most likely places in the solar system to harbor extraterrestrial life. NASA's Europa Clipper mission, launched in 2024, is designed to study Europa's ice shell and ocean, searching for the chemical conditions necessary for life. We may be on the verge of discovering that we are not alone, and the answer might be hiding under the ice of a moon orbiting a gas giant, 778 million kilometers from the Sun. Then there is Io, the most volcanically active body in the solar system. Io is a tortured world, constantly squeezed and stretched by the gravitational tug-of-war between Jupiter and the other large moons. This tidal heating generates so much internal energy that Io's surface is covered in hundreds of active volcanoes, some of which shoot plumes of sulfur and sulfur dioxide hundreds of kilometers into space. Io's surface is constantly being resurfaced by lava flows, so it has essentially no impact craters. They are all covered up. Ganymede, Jupiter's largest moon and the largest moon in the solar system, is even bigger than the planet Mercury. It is the only moon known to have its own magnetic field. And Callisto, the outermost of the 4 Galilean moons, is one of the most heavily cratered objects in the solar system. Its ancient surface a record of billions of years of impacts. Jupiter's moon system is a laboratory of extremes, and each world has its own story to tell. Jupiter also plays a crucial role in the safety of the inner solar system. Its massive gravity acts as a cosmic vacuum cleaner, attracting and deflecting asteroids and comets that might otherwise head toward Earth. Some scientists believe that Jupiter's presence has significantly reduced the number of major impacts on Earth over the past few billion years, giving life more time to evolve without being repeatedly wiped out. In this sense, Jupiter is our protector. And here is one more mind-bending fact. If Jupiter were about 80 times more massive than it is, the pressure and temperature in its core would be sufficient to ignite nuclear fusion. Jupiter would become a star. Our solar system would be a binary star system, and the conditions for life on Earth would be very, very different, if life could exist at all. Jupiter failed to become a star by a wide margin in terms of mass, but the fact that the same basic physics that powers the Sun is at work in Jupiter, just at a smaller scale, is a reminder that planets and stars are not as different as they seem. They exist on a continuum. Now, let us move to what many people consider the most beautiful planet in the solar system, Saturn. If Jupiter is the king, Saturn is the jewel, and that is not just poetry. Saturn's ring system is one of the most visually stunning features in the entire cosmos. Through a telescope, Saturn looks like a work of art, a pale golden sphere encircled by brilliant, perfectly symmetrical rings. The first time I saw Saturn through a telescope, I literally gasped. It does not look real. It looks like something a CGI artist created. But it is real, and it is glorious. Saturn's rings are made primarily of particles of water ice, ranging in size from tiny grains to chunks as large as houses. The rings span about 282,000 kilometers from edge to edge, which is roughly 3/4 of the distance from Earth to the Moon. But here is the astonishing part. Despite their enormous width, the rings are incredibly thin, averaging only about 10 meters thick. If you scaled Saturn's rings down so that their width was the length of a football field, they would be thinner than a sheet of paper. They are unimaginably flat. Where did the rings come from? There are several theories. They may be the remnants of a moon that was torn apart by Saturn's tidal forces, or they may be leftover debris from the formation of the solar system. Recent data from the Cassini mission suggests that the rings are surprisingly young, perhaps only 100 million to 200 million years old, which means that dinosaurs on Earth may have looked up at a Saturn without rings. That is a mind-bending thought. Saturn itself is a gas giant, the second largest planet in the solar system, with a diameter of about 116,460 kilometers. It is famous for being the least dense planet, with an average density of only 0.687 grams per cubic centimeter, less than water. This means that if you could find an ocean large enough, Saturn would float. Let that image sit in your mind for a moment. A planet floating in water like a giant bath toy. Saturn's moon system is as fascinating as Jupiter's. Titan, Saturn's largest moon, is the second largest moon in the solar system and is larger than Mercury. Titan is the only moon with a substantial atmosphere, a thick orange haze of nitrogen and methane that is denser than Earth's atmosphere. Below that atmosphere, Titan has lakes, rivers, and seas of liquid methane and ethane. It rains methane on Titan. There are methane clouds, methane rivers carving channels in the terrain, and vast methane seas near the poles, some larger than the Great Lakes. Titan is essentially an Earth-like world, but with a completely different chemistry, running on hydrocarbons instead of water. The European Space Agency's Huygens probe, which landed on Titan in 2005 as part of the Cassini-Huygens mission, sent back images of a world with rounded pebbles, drainage channels, and a horizon that looked eerily Earth-like. Titan is one of the most alien and yet most familiar worlds we have ever explored. And then there is Enceladus. Tiny Enceladus, only 504 kilometers in diameter, a moon you could drive across in a few hours. Enceladus has become one of the most exciting bodies in the solar system because of what Cassini discovered. Enormous geysers of water vapor and ice particles erupting from cracks near Enceladus's south pole, shooting hundreds of kilometers into space. These geysers are fed by a subsurface ocean of liquid water, kept warm by tidal heating from Saturn's gravity. Cassini flew through the plumes and detected water vapor, organic molecules, molecular hydrogen, and silica nanoparticles, all of which suggest hydrothermal vents on the ocean floor. On Earth, hydrothermal vents support thriving ecosystems of life, completely independent of sunlight. Could the same thing be happening on Enceladus? Could there be microbial life, or even something more complex, swimming in a dark ocean beneath the ice of this tiny moon? It is a genuine possibility, and future missions to Enceladus are being seriously discussed. Saturn also has a hexagonal storm at its north pole, a persistent six-sided cloud pattern roughly 30,000 kilometers across, large enough to fit 4 Earths inside it. Hexagons are extremely unusual in fluid dynamics at this scale, and the exact mechanism that creates and maintains this pattern is still debated. Saturn, like Jupiter, is full of mysteries. The Cassini-Huygens mission, which orbited Saturn from 2004 to 2017, is widely considered one of the greatest space missions ever conducted. It revolutionized our understanding of Saturn, its rings, and its moons. When the mission ended, Cassini was deliberately plunged into Saturn's atmosphere to prevent any possibility of contaminating Titan or Enceladus with Earth microbes. It burned up and became part of Saturn itself. There is something poetic about that, a machine built by humans, launched from Earth, traveling billions of kilometers to explore a world beyond our reach, and finally becoming part of that world forever. Now, let us continue outward, to the 2 ice giants, Uranus and Neptune. These are the forgotten planets, the planets that most people cannot tell apart, the planets that have been visited by only a single spacecraft. And yet, they are among the strangest and most fascinating worlds in the solar system. Uranus is the sideways planet. While every other planet in the solar system rotates roughly upright relative to its orbital plane, Uranus is tilted at 98 degrees. It is essentially rolling around its orbit on its side. The most widely accepted explanation is that early in the solar system's history, Uranus was struck by an Earth-sized body that knocked it over. This extreme tilt has bizarre consequences. During Uranus's 84-year orbit around the Sun, each pole gets about 42 years of continuous sunlight, followed by 42 years of continuous darkness. Uranus is an ice giant, meaning its bulk composition is not primarily hydrogen and helium like Jupiter and Saturn, but rather heavier elements, particularly water, methane, and ammonia, in a hot, dense fluid state. The methane in Uranus's atmosphere absorbs red light and reflects blue light, giving it its distinctive pale blue-green color. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, and it has a faint ring system that was not discovered until 1977. And deep inside Uranus, pressures and temperatures may be high enough to compress carbon into diamonds. It literally rains diamonds inside Uranus. Diamonds, formed from the crushing pressure of the planet's interior, may sink through the layers of exotic ice and accumulate around the core. Scientists have actually replicated this process in the laboratory, compressing carbon at extreme pressures and producing tiny diamonds. On Uranus and Neptune, this process may produce diamonds the size of large gemstones, falling like hailstones through an atmosphere of exotic ice. Only one spacecraft has ever visited Uranus, Voyager 2, which flew past in January 1986. The encounter was brief, and while it returned valuable data and images, our knowledge of Uranus remains limited. There are ongoing discussions about sending a dedicated orbiter to Uranus, which would revolutionize our understanding of this enigmatic world. Uranus is the least explored planet in the solar system, and it deserves more attention. Neptune, the 8th and outermost planet, is the windiest world in the solar system. Despite receiving very little solar energy, being so far from the Sun that it gets roughly 1/900th the solar energy that Earth receives, Neptune has the fastest winds of any planet, up to 2,100 kilometers per hour. Nobody fully understands why. Neptune has less internal heat than Jupiter, yet it somehow generates these extraordinary wind speeds. It is as if a freezer were somehow producing hurricanes. Neptune's deep blue color, even more vivid than Uranus's, comes from the same methane absorption but with some additional, still unidentified component that gives it a richer hue. Neptune takes 165 Earth years to complete a single orbit around the Sun. It was discovered in 1846, which means that as of now, Neptune has completed just about one orbit since humans first knew it existed. Think about that. We discovered Neptune, and it has barely moved. That is how far away it is and how vast its orbit is. Neptune's largest moon, Triton, is one of the most intriguing objects in the solar system. It orbits Neptune backward, in the opposite direction of Neptune's rotation. This retrograde orbit is strong evidence that Triton did not form alongside Neptune but was instead captured. Likely a Kuiper Belt object that strayed too close and was snared by Neptune's gravity. Triton is geologically active, with nitrogen geysers erupting from its surface. It has a thin atmosphere and a young surface with very few craters. Triton may also have a subsurface ocean, adding it to the growing list of ocean worlds in our solar system. Eventually, Triton's retrograde orbit will decay, and in a few billion years it will cross Neptune's Roche limit and be torn apart by tidal forces, potentially forming a new ring system even more spectacular than Saturn's. But we will not be around to see it. And here is the diamond rain fact again, because it deserves emphasis. On both Uranus and Neptune, conditions deep in the atmosphere, thousands of kilometers below the visible cloud tops, may cause carbon atoms to be squeezed together under immense pressure and temperature, forming solid diamonds. These diamonds then sink, like rain, deeper into the planet. This has been simulated in laboratories using high-powered lasers, and it works. There are worlds in our own solar system where it rains diamonds. The universe does not lack for wonders. We have now passed all 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. From the scorched surface of Mercury to the diamond rains of Neptune. It is an extraordinary collection of worlds. But here is what I need you to understand. The solar system does not end at Neptune. Not even close. In fact, by one measure, we have barely begun to cross the solar system. The planets are clustered relatively close to the Sun. The true extent of our Sun's gravitational domain reaches far, far beyond Neptune, into regions so dark and so cold and so distant that we have barely begun to explore them. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies extending from about 30 astronomical units to roughly 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So, the Kuiper Belt begins at about 4.5 billion kilometers from the Sun and extends to roughly 7.5 billion kilometers. It is the realm of Pluto and its brethren, and it holds a special place in the public imagination because of the great Pluto debate. Pluto. Poor, beloved Pluto. Discovered in 1930 by Clyde Tombaugh, Pluto was considered the 9th planet for 76 years. Schoolchildren memorized its name. It was in every textbook. And then, in 2006, the International Astronomical Union reclassified it as a dwarf planet. The reason was the discovery of other Kuiper Belt objects of similar size, particularly Eris, which is actually slightly more massive than Pluto. The IAU decided that to be a planet, a body must meet 3 criteria. It must orbit the Sun, it must be massive enough for gravity to make it roughly spherical, and it must have cleared the neighborhood around its orbit. Pluto meets the first 2 but fails the third. Its orbit crosses Neptune's and is full of other Kuiper Belt objects. The decision was controversial and remains so. Many planetary scientists disagree with it, but regardless of what we call Pluto, the data we have about it is extraordinary. In July 2015, NASA's New Horizons spacecraft flew past Pluto after a journey of 9.5 years and 3 billion miles. What it found was astonishing. Pluto is not the dead, featureless ball of ice that many expected. It is a complex, geologically active world with mountains of water ice as tall as the Rocky Mountains, glaciers of nitrogen ice flowing across its surface, a thin atmosphere of nitrogen with hazes extending hundreds of kilometers above the surface, and a heart-shaped feature, informally named Tombaugh Regio after Pluto's discoverer, that became an instant icon. The left lobe of the heart, called Sputnik Planitia, is a vast plain of nitrogen ice that appears to be remarkably young, with no visible impact craters, suggesting ongoing geological activity. Pluto has 5 known moons, the largest being Charon, which is so big relative to Pluto that the two are sometimes considered a double dwarf planet. New Horizons transformed Pluto from a distant point of light into a real world, a place with personality and surprises. It is one of the most stunning examples of why we explore, because the universe is always more interesting than we expect. The Kuiper Belt contains far more than just Pluto. Eris, Makemake, Haumea, and likely thousands of other objects larger than 100 kilometers populate this region. The total number of objects in the Kuiper Belt larger than 1 kilometer may exceed 100 billion. It is a vast reservoir of primordial material, leftovers from the formation of the solar system that were never swept up into a planet. The Kuiper Belt is also the source of short-period comets, those with orbital periods of less than 200 years. When a Kuiper Belt object is gravitationally perturbed, nudged out of its orbit by the influence of Neptune, it can fall inward toward the Sun, developing the characteristic tail of gas and dust that we call a comet. Beyond the Kuiper Belt, we reach a boundary that marks a profound transition, the heliopause. This is the point where the solar wind, the stream of charged particles constantly flowing outward from the Sun, is finally overcome by the pressure of the interstellar medium, the thin gas and dust that fills the space between stars. The heliopause is the boundary of the heliosphere, the vast bubble of solar influence that surrounds our entire solar system. Crossing the heliopause means leaving the Sun's direct influence and entering interstellar space. Voyager 1, launched in 1977, crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. As of now, Voyager 1 is approximately 24 billion kilometers from Earth, and its signal, traveling at the speed of light, takes more than 22 hours to reach us. Every command we send takes over 22 hours to arrive, and every piece of data it sends back takes another 22 hours. A round-trip communication takes nearly 2 full days. And yet, amazingly, both Voyagers are still functioning, still sending data, still exploring. They are powered by radioisotope thermoelectric generators, which convert the heat from decaying plutonium-238 into electricity. These generators are slowly losing power, and by the mid-2030s there will not be enough electricity to power any scientific instruments. The Voyagers will go silent, but they will continue drifting through interstellar space essentially forever, carrying with them the golden record, a phonograph record containing sounds and images of Earth. Music from Beethoven to Chuck Berry, greetings in 55 human languages, the sound of a heartbeat, a mother's kiss, thunder, bird song, whale song. The golden record was designed as a message in a bottle, cast into the cosmic ocean, a snapshot of human civilization in case any extraterrestrial being should ever find it. The odds are astronomically small, but the gesture is beautiful. But the heliopause is not the true edge of the solar system. Beyond it, far beyond it, lies the Oort cloud, a theoretical sphere of icy bodies that completely surrounds the solar system like a vast, diffuse shell. The Oort cloud is thought to extend from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun, which is nearly 2 light-years, almost halfway to the nearest star. The Oort cloud has never been directly observed. No spacecraft has come anywhere close to it. Voyager 1, the most distant human-made object, will not reach the inner Oort cloud for approximately 300 years. But we know the Oort cloud must exist because of long-period comets. Comets with orbital periods of thousands or even millions of years that come from all directions, not just the plane of the solar system. These comets must originate from a spherical distribution of objects far beyond the Kuiper belt. The Oort cloud may contain trillions of icy bodies, each one a pristine remnant of the solar system's formation, frozen in deep space for billions of years, waiting for a gravitational nudge to send it falling toward the Sun. The Oort cloud represents the true edge of the Sun's gravitational dominance. Beyond it, objects are more influenced by the gravity of other stars and the overall gravitational field of the galaxy. Let me give you a sense of scale here because this is important. If we shrink the Sun down to the size of a grain of sand, Earth would be about 1 inch away from it. Jupiter would be about 5 inches away. Neptune would be about 30 inches away. The Kuiper belt would extend to about 3 feet. But the Oort cloud? The Oort cloud would extend roughly 1 mile in every direction. And the nearest star, Proxima Centauri, it would be about 4 miles away. Think about that model, a grain of sand, with the nearest other grain of sand 4 miles away. And the space in between is not empty, but contains a sparse, invisible cloud of ice extending a mile in every direction. That is our solar system. That is our home. And we are about to leave it behind. We are now at roughly the halfway point of our journey, and I want you to pause and take a breath with me. Think about what we have covered. We started on the surface of Earth and traveled outward past the Moon, the Sun, Mercury, Venus, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, the Kuiper belt, the heliopause, and the Oort cloud. We have covered distances ranging from 100 kilometers to nearly 2 light-years. And here's the thing. We have not even left our own star's gravitational influence yet. Everything we have discussed so far is our solar system, our backyard, and the universe is incomprehensibly larger. The scale is about to increase by factors that your brain genuinely cannot process. If this journey has already been blowing your mind, you need to brace yourself for what is coming next. If you're enjoying this deep dive, and I hope you are, take a second to smash that like button. It genuinely helps the algorithm show this to more people who are curious about the cosmos. And drop a comment right now telling me, which fact so far has been the most mind-blowing for you? Was it the diamond rain on Neptune? The 100,000-year journey of a photon through the Sun? The ice on Mercury? The potential ocean on Enceladus? I want to know. Let me know in the comments. And now, let us step out of the solar system and into the void between stars, interstellar space. The space between the stars. When you look up at the night sky and see those points of light scattered across the blackness, you are not seeing stars floating in a void. Well, you kind of are. But that void is not truly empty. Interstellar space is filled with the interstellar medium, a diffuse mixture of gas, mostly hydrogen and helium, and dust, tiny particles of carbon, silicon, and other elements. But the word filled is extremely generous. The density of the interstellar medium is roughly 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. That is 25 followed by 18 zeros. So, interstellar space is not empty, but it is as close to empty as anything you will ever encounter. It is a vacuum so profound that it would take you years of pumping to achieve it in a laboratory on Earth. And the distances. Oh, the distances. This is where human intuition breaks down completely. We need to talk about the light year because it is the fundamental unit of cosmic distance, and it is mind-breakingly large. 1 light year is the distance that light travels in 1 year. Light moves at approximately 300,000 kilometers per second. In 1 year, that adds up to roughly 9.46 trillion kilometers. 9.46 trillion. That is a 9 followed by 12 zeros. And the nearest star to our Sun, Proxima Centauri, is 4.24 light years away. So the nearest star, the closest one, our immediate next-door neighbor, is about 40 trillion kilometers away. At the speed of our fastest spacecraft, roughly 60,000 kilometers per hour, it would take over 70,000 years to reach Proxima Centauri. 70,000 years. Human civilization is only about 10,000 years old. We would need to travel 7 times the entire span of civilization to reach the nearest star. That is how far apart stars are. That is how empty space is. Proxima Centauri is a red dwarf star, much smaller and cooler and dimmer than our Sun. It is part of a triple star system called Alpha Centauri. The main pair, Alpha Centauri A and Alpha Centauri B, orbit each other closely, while Proxima Centauri orbits the pair at a much greater distance. Alpha Centauri A is remarkably similar to our Sun, a G-type main sequence star of comparable mass and luminosity. It is the closest Sun-like star to us. In 2016, astronomers discovered a planet orbiting Proxima Centauri in the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. This planet, Proxima Centauri b, is roughly Earth-sized and has generated enormous excitement. Could it support life? The challenges are significant. Red dwarf stars like Proxima Centauri are prone to violent flares that could strip a planet's atmosphere and irradiate its surface. Proxima b is also likely tidally locked, meaning one side permanently faces the star while the other is in permanent darkness. Life would have to cope with extreme conditions. But we do not know for certain that life cannot cope. Life on Earth has proven remarkably adaptable. Thriving in boiling volcanic vents, frozen Antarctic ice, and acidic caves. Who are we to say what life can and cannot do? There is a project called Breakthrough Starshot that aims to send tiny, lightweight spacecraft to Proxima Centauri, using light sails accelerated by ground-based lasers. These probes, each weighing only a few grams, would be accelerated to roughly 20% the speed of light, allowing them to reach Proxima Centauri in about 20 years. It is an audacious idea, and the technical challenges are enormous, but it is not science fiction. It is being seriously researched by serious scientists with serious funding. If it works, we could have our first close-up images of another star system within our lifetimes. That possibility alone is worth getting excited about. Beyond Proxima Centauri, the stellar neighborhood opens up. Barnard's star, about 6 light-years away, is a very old red dwarf moving through space faster than any other known star relative to the Sun. Sirius, at 8.6 light-years, is the brightest star in the night sky, a white main sequence star about twice the mass of the Sun, accompanied by a white dwarf companion called Sirius B. Further out, at about 11 light-years, we find Ross 128, another red dwarf with a potentially habitable planet. And at 39 light-years, we find one of the most exciting planetary systems discovered in recent years. TRAPPIST-1. This tiny, ultra-cool red dwarf star has 7 Earth-sized planets orbiting it, 3 of which are in the habitable zone. The TRAPPIST-1 system has been a prime target for atmospheric characterization by the James Webb Space Telescope, which can analyze starlight filtering through a planet's atmosphere to detect molecules like water vapor, carbon dioxide, methane, and oxygen. We are on the verge of being able to detect the chemical signatures of life on planets orbiting other stars. This is not hyperbole. This is happening now, or very close to now. The technology exists. We are looking. And someday, perhaps someday soon, we will find something. But all these stars, Proxima Centauri, Barnard's Star, Sirius, TRAPPIST-1, they are our nearest neighbors. They are the houses on our cosmic street. And our street is a tiny section of a neighborhood. And that neighborhood is a tiny section of a city. And that city is a tiny section of a continent. And that continent is a tiny section of a world. And that world is our galaxy. Let us zoom out and see it all. The Milky Way, our galaxy, our home on the cosmic scale. You have seen it. Or at least you have seen pictures of it. On a dark, clear night, far from city lights, you can see it with your naked eyes. A pale, luminous band stretching across the sky, composed of billions of stars so distant that their individual light merges into a single, soft glow. Ancient peoples called it a river of milk, the road of the gods, the backbone of the night. They did not know what it was. We do. It is the edge-on view of a galaxy, seen from inside. We are embedded in the disk of the Milky Way, so when we look along the plane of the disk, we see a dense concentration of stars. That is the band of light in the sky. It is one of the most beautiful sights in the natural world, and it is a tragedy that most people in the modern world have never seen it due to light pollution. If you have the chance, please go somewhere dark and look up. You will not regret it. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend. It is approximately 100,000 to 180,000 light-years in diameter, depending on how you define the edge. The disk is about 2,000 light-years thick, though the central bulge is considerably thicker. The Milky Way contains between 200 billion and 400 billion stars. That range is not an error. It is a genuine uncertainty, because counting stars in a galaxy you are inside of is extremely difficult. But let us pick a conservative number, 200 billion. 200 billion stars, each one a sun, many with their own planets. If even a tiny fraction of those stars have planets in the habitable zone, and if even a tiny fraction of those planets develop life, the numbers are staggering. There could be millions of civilizations in our galaxy alone, or there could be 0 others. We do not know, and that unknowing is one of the great mysteries of our time. Our sun is located in one of the smaller spiral arms, called the Orion Arm, about 26,000 light-years from the galactic center. We are not at the center. We are not at the edge. We are in the galactic suburbs, roughly 2/3 of the way out from the center. This location may actually be advantageous for life. The galactic habitable zone is a concept suggesting that regions too close to the galactic center are too dangerous, with too many supernovae and too much radiation, while regions too far out lack the heavy elements necessary for rocky planets and complex chemistry. Our position, comfortably in the middle, may be just right for life. Goldilocks again. At the very center of the Milky Way lurks Sagittarius A star, a supermassive black hole with a mass of approximately 4 million times that of the Sun. We cannot see it directly. It is hidden behind vast clouds of gas and dust, but we can detect its presence through its gravitational influence on nearby stars. Astronomers have tracked stars orbiting Sagittarius A star for decades, watching them zip around at incredible speeds. The star S2, for example, orbits Sagittarius A star in about 16 years and reaches speeds of up to 2.55% the speed of light, roughly 7,650 kilometers per second at its closest approach. By tracking these orbits, astronomers Andrea Ghez and Reinhard Genzel were able to precisely measure the mass of the black hole, earning them the Nobel Prize in Physics in 2020. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing the shadow of the black hole surrounded by a glowing ring of superheated gas. It was only the second image of a black hole ever produced, after the image of M87's black hole in 2019. We are living in an age where we can photograph black holes. Let that sink in. Every supermassive black hole is a paradox. It is a region of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon, the point of no return. Inside the event horizon, our current understanding of physics breaks down. General relativity predicts a singularity, a point of infinite density, at the center. But infinite density probably does not actually exist. It is more likely a sign that our theories are incomplete, that we need a theory of quantum gravity to understand what really happens inside a black hole. The information paradox, one of the deepest puzzles in modern physics, asks, what happens to the information about everything that falls into a black hole? Does it disappear? Is it preserved? Stephen Hawking spent decades wrestling with this question, and it remains unresolved. Black holes are not just astronomical objects, they are laboratories for the most fundamental questions in physics. The Milky Way is also full of nebulae, vast clouds of gas and dust where stars are born and where they die. Stellar nurseries like the Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation of Orion, are regions where gravity is pulling gas together, collapsing it into denser and denser clumps that will eventually ignite as new stars. The Eagle Nebula contains the famous Pillars of Creation, towering columns of gas and dust photographed by the Hubble Space Telescope in one of the most iconic images in astronomical history. These pillars are light years tall and are being sculpted by the intense radiation of nearby young stars. Deep inside them, new stars are forming. It is creation happening in real time, albeit on timescales of millions of years. Stars are born, they live, and they die, and the way they die depends on how massive they are. Stars like our Sun will swell into red giants, shed their outer layers into planetary nebulae, and fade as white dwarfs. But massive stars, those with more than about 8 times the mass of the Sun, die spectacularly. When they exhaust their nuclear fuel, their cores collapse in a fraction of a second, and the resulting rebound produces a supernova, an explosion so powerful that, for a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. Supernovae are the most energetic events in the universe short of the Big Bang itself, and they are absolutely crucial for our existence. Here is why. The nuclear fusion in a star's core can produce elements up to iron on the periodic table. But everything heavier than iron, gold, silver, platinum, uranium, the elements that make up so much of our technology and our world, these can only be created in the extreme conditions of a supernova explosion, or in the collision of neutron stars. So every gold atom in every wedding ring, every piece of jewelry, every electronic device, was forged in the death throes of a star that exploded billions of years ago. The carbon in your body was made in a star. The iron in your blood was made in a star. The calcium in your bones was made in a star. You are literally, physically, chemically made of star stuff. This is not poetry. This is chemistry. This is physics. You are the universe experiencing itself through atoms that were cooked up in nuclear furnaces that no longer exist. After a supernova, the core of the massive star can collapse into one of two things, depending on its mass. If the remaining core is between about 1.5 and 3 solar masses, it becomes a neutron star, an object so dense that a teaspoon of a neutron star material would weigh about 6 billion tons. A neutron star is essentially a giant atomic nucleus, about 20 kilometers in diameter, spinning at incredible rates, sometimes hundreds of times per second. Some neutron stars emit beams of radiation from their poles, and if those beams sweep across Earth like a lighthouse, we detect them as pulsars, rapidly repeating radio signals that were initially mistaken for alien communications. When neutron stars were first discovered in 1967, the regular, repeating signal was so unexpected that the discoverers, Jocelyn Bell Burnell and Anthony Hewish, jokingly labeled the signal LGM1 for Little Green Men. It was not aliens. It was something equally remarkable. A dead star, spinning 30 times per second, screaming into the void. If the remaining core is more than about 3 solar masses, not even the repulsive force between neutrons can resist the crush of gravity. The core collapses beyond the neutron star stage, forming a stellar mass black hole. These black holes range from about 5 to several dozen solar masses and are scattered throughout the galaxy. We detect them primarily when they are in binary systems, pulling gas from a companion star, which forms a swirling disk of superheated material called an accretion disk that emits X-rays we can observe with space telescopes. The Milky Way likely contains hundreds of millions of stellar mass black holes. The Milky Way is not static, it is rotating. Our Sun orbits the galactic center at about 828,000 kilometers per hour, and even at that tremendous speed, it takes approximately 225 to 250 million years to complete one orbit. This period is sometimes called a galactic year, or a cosmic year. The Sun is about 4.5 billion years old, so it has completed roughly 18 to 20 orbits around the galaxy in its lifetime. Dinosaurs roamed the Earth about 1 galactic year ago. The last time the Sun was in this part of the galaxy, dinosaurs did not exist yet. Time moves differently on galactic scales. And the Milky Way is not alone. It is gravitationally bound to a collection of other galaxies called the local group, and this is where our cosmic context begins to expand dramatically. The local group is a collection of more than 80 galaxies bound together by gravity, spanning roughly 10 million light-years. It is dominated by 2 large spiral galaxies, our Milky Way and the Andromeda Galaxy, also known as M31. The third largest member is the Triangulum Galaxy, M33, a smaller spiral. The rest are mostly dwarf galaxies, small, dim collections of a few billion stars or less, many of which orbit the larger members as satellites. The Milky Way has dozens of known satellite galaxies, including the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere and are among the closest galaxies to us, at about 160,000 and 200,000 light-years respectively. The Andromeda Galaxy is a special case, and it deserves special attention because it is on a collision course with the Milky Way. Right now, Andromeda is approximately 2.5 million light-years away. When you look at it in the night sky and you can see it with the naked eye under dark skies as a faint fuzzy patch, you are seeing light that left Andromeda 2.5 million years ago, when our ancestors were just beginning to use stone tools. It is the most distant object visible to the unaided human eye. Andromeda is larger than the Milky Way, roughly 220,000 light-years across, and contains approximately 1 trillion stars. And it is approaching us at about 110 kilometers per second. In about 4.5 billion years, the Milky Way and Andromeda will collide. When galaxies collide, it is not the violent, explosive event you might imagine. The space between stars is so vast that the chances of any two stars actually hitting each other are negligible. Instead, the two galaxies will pass through each other, their gravitational interactions pulling long tails of stars out into space, then swing around and pass through each other again and again over the course of billions of years, gradually merging into a single, large elliptical galaxy that astronomers have already nicknamed Milkomeda or Milkdromeda. The night sky of that distant future will be very different from ours. Instead of the elegant band of the Milky Way, it will be dominated by a vast, featureless blob of stars. The Milky Way is also actively consuming smaller galaxies right now. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is currently being torn apart and absorbed by the Milky Way. Its stars are being stretched into long streams that wrap around our galaxy. This is a process called galactic cannibalism, and it is completely normal. Large galaxies grow by consuming smaller ones. The Milky Way has done it many times before and will do it again. In the grand scheme of things, the Milky Way is both predator and prey. It eats dwarf galaxies and will eventually be consumed by its merger with Andromeda. But the local group is just a tiny cluster. It is a small town. Let us zoom out to the city, the county, the state. Let us see the larger structures. The local group is part of a larger structure called the Virgo supercluster, named after the Virgo cluster of galaxies, which is the nearest large galaxy cluster to us. The Virgo cluster is located about 54 million light-years away and contains between 1,300 and 2,000 galaxies, many of them large elliptical and spiral galaxies. At the center of the Virgo cluster sits M87, a giant elliptical galaxy that became famous in 2019 when the Event Horizon Telescope produced the first ever image of a black hole. A supermassive black hole at M87 center with a mass of 6.5 billion solar masses. 6.5 billion, not million, billion. That single black hole has 1,500 times the mass of the supermassive black hole at the center of our own galaxy. M87's black hole is a monster among monsters. Galaxy clusters are the largest gravitationally bound structures in the universe. They are held together by gravity, their constituent galaxies orbiting within a vast halo of hot gas and dark matter. The gas between galaxies in a cluster, called the intracluster medium, is heated to tens of millions of degrees by gravitational compression and emits X-rays that we can detect with space telescopes like Chandra. Galaxy clusters are also among the most powerful gravitational lenses in the universe. Einstein's general relativity predicts that massive objects bend the fabric of space-time, and this bending causes the light from more distant objects to be distorted and magnified. When a galaxy cluster sits between us and a more distant galaxy, the cluster's gravity can bend the light around it, creating arcs, rings, and multiple images of the background galaxy. This is called gravitational lensing, and it is not just a beautiful effect, it is a powerful tool for measuring the distribution of dark matter, which we cannot see directly but whose gravity does the lensing. The Virgo supercluster itself is part of an even larger structure. In 2014, a team of astronomers led by Brent Tully published a groundbreaking paper that redefined our understanding of the cosmic neighborhood. Using data on the velocities and positions of thousands of galaxies, they mapped the flows of galaxies, the way galaxies are moving through space, under the influence of gravity. They discovered that the Virgo supercluster is just one lobe of a much larger supercluster, which they named Laniakea, from the Hawaiian for immense heaven. Laniakea contains approximately 100,000 galaxies, spans about 520 million light-years, and has a total mass of roughly 10 to the 17th solar masses, which is 100 quadrillion times the mass of the Sun. Within Laniakea, all galaxies are flowing toward a region called the Great Attractor, a gravitational anomaly that has been puzzling astronomers since the 1970s. The Great Attractor is located roughly 250 million light-years away, in the direction of the constellation Centaurus and Norma, but we cannot observe it directly because it lies behind the zone of avoidance, the region of the sky obscured by the dense stars, gas, and dust of the Milky Way's own disk. We know it is there because of its gravitational pull on everything around it, but we cannot see what it is. It is likely a massive concentration of galaxy clusters, possibly the core of a super-supercluster, but its exact nature remains mysterious. Beyond Laniakea, there are other superclusters. The Shapley supercluster, located about 650 million light-years away, is one of the most massive concentrations of galaxies in the observable universe and may be contributing to the gravitational pull attributed to the Great Attractor. The Perseus-Pisces supercluster, the Horologium Reticulum supercluster, the Coma supercluster, they are all out there, each one a collection of thousands to hundreds of thousands of galaxies, spread across hundreds of millions of light-years. And they are all connected. They are all part of something bigger. We have arrived at the cosmic web, the largest scale structure in the universe, and it is perhaps the most awe-inspiring thing we will encounter on this entire journey. If you could somehow zoom out far enough, far beyond individual galaxies, beyond galaxy clusters, beyond superclusters, and see the universe on its grandest scale, you would see a pattern. The universe is not random. It is not a uniform, featureless soup of galaxies. It has structure, and that structure looks remarkably like a web, or a network of neurons, or the branching pattern of a tree. The cosmic web consists of filaments, long thread-like structures made of galaxies and dark matter, stretching across hundreds of millions or billions of light-years, connecting galaxy clusters at their intersections like the strands of a spider's web. Between the filaments are vast, almost empty regions called cosmic voids, enormous bubbles of near-nothingness that can be hundreds of millions of light-years across. The origin of the cosmic web lies in the earliest moments of the universe. When the universe was very young, less than a second old, tiny quantum fluctuations, random variations in the density of matter, were stretched to cosmic scales by the rapid inflation of space. These fluctuations, imprinted on the cosmic microwave background radiation that we can still observe today, served as the seeds of all structure in the universe. Regions that were slightly denser than average attracted more matter through gravity, becoming even denser over time. Regions that were slightly less dense lost matter to their denser neighbors and became emptier. Over billions of years, gravity amplified these tiny initial differences into the vast cosmic web we see today. The filaments are where matter accumulated, the voids are where it did not. And at the intersections of filaments where the most matter piled up, we find the largest galaxy clusters. The largest known structures in the cosmic web are genuinely mind-boggling in scale. The Hercules Corona Borealis Great Wall, discovered in 2013, is a vast structure of galaxies spanning roughly 10 billion light-years across. To put that in perspective, the observable universe is about 93 billion light-years across, so this single structure occupies a significant fraction of the observable universe. The Sloan Great Wall, discovered in 2003, spans about 1.37 billion light-years. The BOSS Great Wall, identified in 2016, is another enormous structure. These walls and filaments of galaxies are the largest things in the universe, and their existence poses interesting questions about the cosmological principle. the assumption that on the largest scales, the universe is the same everywhere. How large does a structure have to be before it violates this principle? We are still working that out. And then there are the voids. The cosmic voids are the opposite of the filaments, vast, nearly empty regions where very few galaxies exist. The Botas void, discovered in 1981, is roughly 330 million light-years across and contains only about 60 galaxies. A region that size should contain roughly 2,000 galaxies. The Botas void is sometimes called the Great Nothing. If you were on a planet inside the Botas void, the night sky would be almost completely dark. There would be no Milky Way, few visible stars, just blackness. It would be profoundly lonely. Even more intriguing is the KBC void, discovered in 2013, which suggests that our local group, and in fact our entire region of the universe for about 2 billion light-years in every direction, is inside a giant void, a region that is less dense than the cosmic average. If this is true, it could affect our measurements of the expansion rate of the universe and might help resolve the Hubble tension, a persistent discrepancy between different methods of measuring how fast the universe is expanding. We might be living inside a cosmic bubble, and that bubble might be subtly warping our view of the universe. Dark matter plays a crucial role in all of this. The cosmic web is scaffolded by dark matter. Galaxies and galaxy clusters form along the densest filaments of dark matter, like dewdrops on the strands of a spider's web. Computer simulations of cosmic structure formation, such as the Illustris simulation and the Millennium simulation, model the evolution of dark matter and ordinary matter from the early universe to the present day. When you compare these simulations to actual observations of the cosmic web, the agreement is remarkable. The simulations reproduce the filamentary structure, the voids, the galaxy clusters, even the statistical properties of galaxy distributions, with stunning accuracy. This is one of the strongest pieces of evidence for the existence of dark matter. Without it, the cosmic web cannot be explained. Ordinary matter alone does not have enough mass or the right properties to form the structures we observe. Dark matter provides the gravitational skeleton upon which the visible universe is built. We are approaching the largest scale now. We are about to consider the observable universe itself, the entirety of everything we can see, everything we can detect, everything that light has had time to bring to our attention in the 13.8 billion years since the universe began. This is the cosmic horizon, and understanding it requires us to grapple with some deeply counterintuitive concepts. The observable universe has a diameter of approximately 93 billion light-years. Immediately, this should strike you as strange. The universe is 13.8 billion years old. Light travels at the speed of light, by definition. So, you might expect that we can see 13.8 billion light-years in every direction, giving the observable universe a diameter of 27.6 billion light-years. But it is 93 billion. How? The answer is the expansion of space. The universe has been expanding since the Big Bang. When a photon was emitted by a distant galaxy, say 13 billion years ago, both we and that galaxy were much closer together. But as the photon traveled toward us, the space between us and the galaxy was expanding, carrying the galaxy further away. By the time the photon reaches us, the galaxy that emitted it is no longer 13 billion light-years away. It is much further, because space has been stretching the whole time. The objects at the edge of our observable universe emitted their light about 13.8 billion years ago, but they are now approximately 46.5 billion light-years away from us, because space has been expanding continuously. Multiply by 2 to get the full diameter, and you get 93 billion light-years. The observable universe is larger than the age of the universe would naively suggest, because the universe has been expanding while the light was in transit. This is not about objects moving through space faster than light, which is impossible. It is about space itself expanding, and there is no speed limit on the expansion of space. What is in the observable universe? Let us take stock. According to current estimates, the observable universe contains approximately 2 trillion galaxies. 2 trillion. That number was revised upward significantly in 2016, based on deep surveys by the Hubble Space Telescope, combined with mathematical models. Many of these galaxies are too small and too faint to see with current telescopes, but they are there. Each galaxy contains anywhere from a few million to over 1 trillion stars. In total, the observable universe contains roughly 200 billion trillion stars, which is a 2 followed by 23 zeros. That number is often compared to the number of grains of sand on all the beaches on Earth, and the stars win. There are more stars in the observable universe than grains of sand on every beach on this planet. And most of those stars have planets. Current estimates suggest that on average, each star in the Milky Way has at least 1 planet, and the same is likely true for other galaxies. That gives us roughly 200 billion trillion planets in the observable universe. The sheer number of chances for life to arise is staggering. The composition of the observable universe, by mass and energy, is one of the most humbling facts in all of science. Ordinary matter, the stuff you and I are made of, the stuff that makes up stars, planets, gas clouds, everything we can see and touch and measure, accounts for only about 5% of the total mass energy content of the universe. Dark matter, the invisible substance whose gravity holds galaxies and clusters together, accounts for about 27%. And the remaining 68%? That is dark energy, the mysterious force driving the accelerating expansion of the universe. So, everything we have talked about in this entire video, every star, every planet, every galaxy, every structure, all of it, constitutes 5% of the universe. The other 95% is stuff we cannot see, cannot touch, and barely understand. We are a minority component in our own universe. We are the foam on the cosmic ocean. The cosmic microwave background radiation is the oldest light in the universe, and it is one of the most important observations in all of cosmology. It was emitted about 380,000 years after the Big Bang, at a time called recombination, when the universe cooled enough for electrons to bind to protons and form neutral hydrogen atoms. Before this moment, the universe was a hot, opaque plasma, like the interior of a star, with photons constantly scattering off free electrons. But when neutral atoms formed, the photons were finally free to travel through space unimpeded. Those photons have been traveling ever since, for 13.8 billion years, and they fill the entire universe. They are everywhere. They are hitting you right now, passing through you, all around you, in every direction. If you tune an old analog television to a channel with no signal, a small percentage of the static you see is caused by cosmic microwave background photons. You are literally watching the afterglow of the Big Bang. The CMB was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, 2 radio astronomers at Bell Laboratories in New Jersey. They were using a large horn antenna to make radio observations and found a persistent background noise that they could not eliminate. They checked everything. They rebuilt equipment. They famously found pigeons nesting in the antenna and cleaned out the droppings, thinking that might be the source. Nothing worked. The noise was everywhere, in every direction, at every time of day and night. It was a uniform microwave signal with a temperature of about 3 Kelvin, negative 270 degrees Celsius. It was the CMB, and its discovery earned Penzias and Wilson the Nobel Prize. They had found the oldest light in the universe by accident, while trying to get rid of what they thought was interference. Since then, the CMB has been mapped with increasing precision by satellites including COBE in 1989, WMAP in 2001, and Planck in 2009. Each generation of satellites revealed finer and finer details in the CMB, showing tiny temperature fluctuations of about 1 part in 100,000. These fluctuations are the fingerprints of the quantum fluctuations from the early universe that grew, through gravity, into the cosmic web of galaxies and clusters that we see today. The CMB is not just a picture of the early universe. It is the blueprint of everything that exists. Every galaxy, every star, every planet, every person was encoded in those tiny temperature variations 380,000 years after the Big Bang. We can trace our lineage, the lineage of everything, back to quantum fluctuations in a hot, dense plasma nearly 14 billion years ago. The expansion of the universe was first discovered by Edwin Hubble in 1929. By observing distant galaxies and measuring both their distances and their velocities, Hubble found a remarkable correlation. The further away a galaxy is, the faster it is moving away from us. This relationship, known as Hubble's law, was the first observational evidence that the universe is expanding. But it is crucial to understand what expanding means in this context. The galaxies are not flying apart through space like shrapnel from an explosion. Space itself is expanding, carrying the galaxies with it. The classic analogy is a loaf of raisin bread baking in an oven. As the bread expands, every raisin moves further from every other raisin. From the perspective of any single raisin, all the other raisins are receding, and the more distant ones are receding faster. There is no center to the expansion. Every point in the universe sees every other point moving away. This is the expansion of the universe, and it has been happening since the Big Bang. The cosmological principle states that, on sufficiently large scales, the universe is homogeneous, the same everywhere, and isotropic, the same in every direction. There is no center of the universe. There is no edge. Every point in the universe is, in a sense, the center of its own observable universe, because every point has a sphere of light around it that defines the furthest distance from which light has had time to arrive. Your observable universe is centered on you. Mine is centered on me. An alien on a planet in the Andromeda Galaxy has its own observable universe. Centered on it, overlapping mostly with ours, but slightly different at the edges. The observable universe is not the universe. It is just the part we can see from our particular location. The actual universe may be much, much larger. We have reached the edge of the observable universe, the furthest we can see, the cosmic horizon. But the universe does not stop here. We know this because there is no reason for it to stop here. The edge of the observable universe is not a wall, not a boundary, not a physical barrier of any kind. It is simply the limit of how far light has had time to travel since the Big Bang. Beyond our cosmic horizon, there is almost certainly more universe, more galaxies, more stars, more planets, more cosmic web, more voids, stretching out further and further. How much further? This is one of the deepest questions in cosmology, and the honest answer is we do not know, and we may never know. Based on measurements of the curvature of space, which can be inferred from the CMB, the universe appears to be spatially flat, or extremely close to flat. A flat universe can be either finite or infinite, but many cosmological models favor an infinite universe. If the universe is infinite, then it goes on forever, in every direction. without end. There is no edge, no boundary, no wall. There is just more and more universe, stretching out to infinity. And in an infinite universe, everything that can happen does happen somewhere. Given enough space, every possible arrangement of atoms occurs. This leads to a staggering implication. In an infinite universe, there may be another planet exactly like Earth, with another person exactly like you, reading this exact same script right now. In fact, there would be infinitely many such copies. This is not mysticism. This is a logical consequence of infinite space and a finite number of possible arrangements of matter. Whether it is actually true depends on whether the universe is actually infinite, which we do not know for certain. But the possibility is there, and it is one of the most mind-bending ideas in all of science. Even if the universe is finite, it may be extraordinarily large. Some estimates, based on the observed flatness of the CMB, suggest that the actual universe could be at least 250 times larger in diameter than the observable universe. That would make the full universe at least 23 trillion light-years across. And some models of cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, suggest that the actual universe could be incomprehensibly larger than that, perhaps 10 to the power of 10 to the power of 10 to the power of 122 times larger. That number is so large that it is meaningless to the human mind. It is beyond comprehension. It is beyond mathematics almost. It is just big, incomprehensibly, absurdly, overwhelmingly big. And here is what makes this even more disorienting. The expansion of the universe is accelerating, which means that the cosmic horizon, the boundary of our observable universe, is not growing as fast as the universe is expanding. Distant galaxies are being carried away from us by the expansion of space faster than light from them can reach us. There are galaxies that we can currently see, galaxies whose light has already reached us, that we will never receive new light from, because the space between us and them is expanding too rapidly. They are crossing our cosmic event horizon, the point beyond which even light emitted now will never reach us. These galaxies will appear to redshift toward infinity, their light stretching to longer and longer wavelengths, becoming dimmer and dimmer, until they fade from view entirely. In the far future, trillions of years from now, the observable universe will contain only our local group of galaxies, which will have merged into a single large elliptical galaxy. Everything else will have faded beyond the cosmic horizon. A civilization arising in that distant future will look out at the sky and see only their own galaxy, surrounded by empty blackness. They will have no evidence that other galaxies ever existed. They will have no way to discover the Big Bang. They will have no way to understand the true nature and history of the universe. The evidence will be gone, carried away by the expansion of space. We are living in a privileged time, a window in cosmic history, when the evidence for the Big Bang and the large-scale structure of the universe is still visible. That window will not remain open forever. Now, let us go back. Back to the beginning, back to the very first moment, back to the event that started everything. Let us talk about the Big Bang. 13.8 billion years ago, something happened. We call it the Big Bang, but that name is misleading. It was not big in the conventional sense, and it was not a bang in any conventional sense. It was not an explosion in space. It was the beginning of space, and time, and matter, and energy, and the laws of physics themselves. Before the Big Bang, there was no before, because time itself began with the Big Bang. The question, what happened before the Big Bang, may be as meaningless as the question, what is north of the North Pole? There is no answer. not because we do not know, but because the question may not have a valid answer. At the moment of the Big Bang, or as close to it as our physics can describe, the entire observable universe, all 93 billion light-years of it, was compressed into a region smaller than a single atom. The temperature was incomprehensibly high, beyond anything our physics can calculate. The density was beyond anything we can imagine. All four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. Our current physics cannot describe this state. We do not have a theory of everything that unifies all four forces. General relativity describes gravity. The standard model of particle physics describes the other three. But at the energy scales of the Big Bang, we need a theory that combines them, a theory of quantum gravity, and we do not have one yet. The Big Bang is, in a sense, the greatest unsolved mystery in physics. The earliest moment we can describe with any confidence is the Planck epoch, from time 0 to about 10 to the negative 43 seconds, the Planck time. This is the smallest meaningful unit of time in physics. Before the Planck time, our understanding of the laws of physics breaks down completely. We do not know what happened. We cannot even speculate meaningfully. It is a blank, a mystery, a wall beyond which our knowledge cannot penetrate. After the Planck time, things begin to happen, and they happen fast, incredibly fast. Between about 10 to the negative 36 seconds and 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of cosmic inflation, a brief but extraordinarily violent expansion in which space itself expanded exponentially. In this inconceivably tiny fraction of a second, the universe grew from a region smaller than a proton to a region larger than the entire observable universe today. Inflation is the most extreme event in cosmic history. It took quantum fluctuations, random variations in energy at the subatomic scale, and stretched them across cosmic distances. These stretched quantum fluctuations became the seeds of all structure in the universe, the tiny density variations that gravity would later amplify into galaxies, clusters, and the cosmic web. Inflation also explains several puzzles about the universe: why it appears so flat, why the CMB temperature is so uniform across the sky, and why we do not observe certain exotic particles predicted by some theories of particle physics. Inflation is not just a theory, it is a theory that makes predictions, and those predictions have been confirmed by observations of the CMB with remarkable precision. After inflation, the universe was filled with a hot, dense soup of fundamental particles, quarks, leptons, gauge bosons, and their antimatter counterparts. The universe was so hot that particles and antiparticles were constantly being created and destroyed in pairs. But there was a tiny asymmetry. For every billion antiparticles, there were 1,000,000,001 particles. Nobody knows why this asymmetry exists. It is one of the great unsolved problems in physics, called baryogenesis. But because of this tiny excess, when all the matter and antimatter annihilated each other, the matter that was left over, that 1/1000,000th excess, is everything we see in the universe today. Every star, every planet, every atom in your body is the leftovers of a cosmic matter-antimatter war that matter won by the slimmest possible margin. At about 1 microsecond after the Big Bang, the universe had cooled enough for quarks to bind together into protons and neutrons. At about 1 second, the universe was a blazing plasma of protons, neutrons, electrons, neutrinos, and photons, with a temperature of about 10 billion degrees. Between about 10 seconds and 20 minutes after the Big Bang, a process called Big Bang nucleosynthesis occurred. Protons and neutrons fused together to form the nuclei of the lightest elements: hydrogen, mostly, about 75% by mass, helium, about 25%, and tiny trace amounts of lithium and deuterium. Heavier elements were not formed because the universe was expanding and cooling too rapidly for the necessary nuclear reactions to occur. All the heavier elements would have to wait for the first stars. But the prediction of Big Bang nucleosynthesis, the specific ratios of hydrogen, helium, and lithium produced, matches observations with impressive accuracy. It is one of the strongest pieces of evidence for the Big Bang. For the next 380,000 years, the universe was a hot, opaque fog. Photons could not travel far before being scattered by free electrons. The universe glowed uniformly, like the inside of a star, but there was nothing to see because light could not travel in straight lines. Then, at 380,000 years, the universe cooled to about 3,000 Kelvin, cool enough for electrons to bind to atomic nuclei and form neutral atoms. This event, called recombination, was a phase transition, like steam condensing into water. Suddenly, the universe went from opaque to transparent. Photons were freed, and they have been traveling through space ever since. Those photons are the cosmic microwave background, the oldest light in the universe, now cooled by the expansion of space from 3,000 Kelvin to just 2.725 Kelvin. When we look at the CMB, we are looking at the universe as it was 380,000 years after the Big Bang. We are looking at the surface of last scattering, the moment when the universe became transparent. It is the earliest snapshot of the universe we can take with light. After recombination, the universe entered the cosmic dark ages, a period lasting roughly 100 to 200 million years during which no stars existed. The universe was filled with neutral hydrogen gas, cooling and darkening, illuminated only by the fading glow of the CMB. There was no light from stars, no galaxies, no structure on small scales, just a vast, dark, slowly cooling fog of hydrogen. Then, gradually, gravity began its work. The densest regions of gas, seeded by those primordial quantum fluctuations, began to collapse under their own gravity. The gas heated as it compressed. And eventually, the first stars ignited. This moment is called cosmic dawn, and it ended the dark ages with the light of the first stars. These first stars, called population 3 stars, were unlike anything in the universe today. They were made entirely of hydrogen and helium, with no heavier elements because no heavier elements existed yet. Without heavier elements to help cool the gas during collapse, these stars formed from much larger clouds and were consequently enormous, perhaps hundreds of times the mass of the Sun. They were incredibly hot, incredibly luminous, and incredibly short-lived, burning through their fuel in just a few million years before exploding as the first supernovae. Those supernovae seeded the universe with the first heavy elements, the first carbon, oxygen, silicon, iron, gold, all forged in the cores and explosions of those first-generation stars. The next generation of stars, population 2, formed from gas enriched with these heavy elements, and they in turn lived and died and enriched the gas further. Eventually, the gas was enriched enough to form population 1 stars, like our Sun, with the full range of heavy elements necessary for rocky planets and complex chemistry. We are third-generation star stuff. The first galaxies formed within the first 500 million to 1 billion years after the Big Bang. The James Webb Space Telescope, launched in December 2021, has been peering back to this epoch, observing galaxies that existed when the universe was only a few 100 million years old. Some of its findings have been surprising. Galaxies that are larger and more mature than expected at such early times, challenging our models of galaxy formation. The universe, it seems, got to work building galaxies faster than we thought possible. Every observation we make of the early universe reveals new surprises. The story is not finished being written. Over the next 13 billion years, the universe evolved into its present state. Galaxies merged and grew. Stars lived and died, generation after generation, each generation enriching the interstellar medium with heavier elements. Galaxy clusters formed at the intersections of the cosmic web. Supermassive black holes grew at the centers of galaxies, fed by infalling gas and galaxy mergers. About 9.2 billion years after the Big Bang, in an unremarkable part of an unremarkable spiral arm of an unremarkable galaxy, a cloud of gas and dust collapsed and formed a star, our Sun, and the disk of debris around it coalesced into planets, including a small rocky world in the habitable zone that we call Earth. About 4 billion years after that, on the surface of that world, microscopic life appeared, evolved, diversified, and eventually produced a species capable of looking up at the sky and asking, "Where did all of this come from?" And that brings us to the great mystery that has been hovering over this entire journey, the force that is shaping the ultimate fate of everything: dark energy. In 1998, two independent teams of astronomers made a discovery that rocked the foundations of cosmology. They were studying Type 1a supernovae, a particular type of stellar explosion that always reaches roughly the same peak brightness, making them useful as standard candles, objects of known luminosity that can be used to measure cosmic distances. By comparing the observed brightness of distant Type 1a supernovae to their expected brightness, and by measuring their redshift to determine how fast the universe was expanding when the light was emitted, these teams hoped to measure the rate at which the expansion of the universe was slowing down. Because gravity pulls matter together, and the universe is full of matter, the expansion should be decelerating. That was the expectation. The data said otherwise. The expansion of the universe is not slowing down, it is speeding up. Distant supernovae were dimmer than expected, meaning they were further away than expected, meaning the expansion of the universe had been accelerating. Something was pushing the universe apart, counteracting gravity, and doing so with increasing vigor. The leaders of these two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, received the Nobel Prize in Physics in 2011 for this discovery. It is arguably the most important cosmological discovery since Hubble's original observation of the expansion itself.